All right, here we go. So for number 6, we have a mass is placed at the free end of a compressed spring whose spring constant is 115 newtons per meter. The spring is compressed 0.2 meters from its neutral position. How much elastic energy is stored? So first what we need to do is sketch out our picture. Okay, so I'll use this. And so we're going to have, I'm just going to put our ground here. All right, and so we have something, and we have a spring. Okay, and attached to the spring is this mass. Okay. All right, there's our mass. Okay, and it is compressed, so that means this is smushed in. Okay, and so we want to find out what the unknown is. So how much elastic energy is stored? So our unknown is going to be our elastic energy. And now we are going to continue with our problem by writing down all the things that we do know. So we have a mass that is, so we have a mass, and we don't really need to know the mass. We just need to know that the mass is compressing the spring, okay? So we don't need that, but we do know that the spring constant is, and let me just erase this mass. Okay, the spring constant is 115 newtons per meter. And the spring is compressed 0.2 meters. So that means that the delta x, so it's the spring compression, is 0.2 meters from its neutral position. And the equation that we're going to be using for this problem is our elastic potential energy is equal to 1/2 spring constant times stretch squared. All right, so now we're going to go ahead and isolate for our problem. Well, we actually don't need to isolate since EE is already on the side by the equal sign by itself. So we have 1/2 kx squared. We're going to replace the k value with whatever we have. So we have 1/2 115 newtons per meters times the spring compression of 0.2 meters squared. All right, and so we have 1/2. So first what we're going to do is square this number. So we have 1/2 times 115 newtons per meter times 0.2 times 0.2 is going to be 0.04 meters squared. All right, so the next thing is we have an elastic energy of, so one of these actually cancels out and this one cancels out. So we have 1/2 times 115 times 0.04 is going to give us 2.3 joules. Okay. So then the proportional reasoning is given the same spring constant. So now our spring constant is going to stay the same. So that stays at 1. What is the elastic energy? So this is the thing that we don't know. Elastic energy. If the spring is compressed to 0.8, so we started off with 0.2 meters, and we're going to 0.8. So 0.2 times something is going to give us 0.8, which is times 4. So our compression is going to quadruple. And so we have 4 squared times 1 is going to be 16. Okay, so we have 16 times EE. We have 16 times our original value of 2.3 joules. So 2.3 times 16 is going to give us 36.8 joules. In the next problem, given the same spring constant, so once again, our spring constant is going to stay the same. What is the distance that the spring is compressed if the elastic energy is quadrupled? So we're going to quadruple this, and now we don't know what this is. So this is going to go here. Okay. So our problem is 4 times something. So 4 is equal to 1 times, or I'll use a dot. times something squared. So we can get rid of the 1, right? So it's just really 4 is equal to x squared. And we're going to square root both sides. So we have 4, or it's square root of 4, sorry. Square root of 4 is 2. 2 is equal to x. So 2. So when we go 2 times 2, because of the square here, we're going to get 4. So that's why our coefficient is 2. So 2 times our original compression of 0.2. I'm sorry. So 0.2 meters, we're going to get 0.4 meters. Okay, and that is number 6.